Hello friends, so today we are going to solve 3 questions, and these 3 questions will be from electrostatics. So in the first question it states that an infinite cylinder with uniform volume charge density rho has its axis lying along z-axis. A sphere is carved out of the cylinder and then filled up with a material of a uniform density minus rho by 2. Assume that the center of the sphere is located on the x-axis at position x equal to a. Show that inside the sphere the component of the field in the xy plane is uniform and find its value. One second. So in this case we have to so we have a cylinder, and from the cylinder we removed a sphere and then filled up with a material with a uniform density of minus rho by 2. So in this case we usually solve the questions in which we remove something but we do not add into. Okay, but in this particular case we are removing a part of the cylinder as a sphere and we are filling that empty space by another material which is having a uniform density of minus rho by 2. Okay. So in this case we are going to obviously using the principle of superposition, okay, or we can say simple superposition. And superposition, so we are going to use superposition. And this superposition we can say we are going to use in 3 steps. So in step number 1 we are going to start with our original cylinder of charge density rho. So we are going to start with original infinite cylinder with the charge density as rho. This is step number 1. And step number 2 we are going to remove the sphere of charge density rho. We are going to remove the sphere of charge density rho. And usually we deal with the numerical in which there are only 2 steps. Okay, we have the original thing and we remove something from that. But in this case we have a third thing also, and in third thing we add back a sphere with charge density and that charge density is given to us as minus rho by 2. So whenever we remove a charge density of rho, so we are going to assume that in that place there is a charge density of minus rho. Okay, that is our usual standard step. Okay. So it means by using our superposition, we can say that the effective charge distribution effective charge distribution inside the spherical region we can write that charge distribution as cylinder of charge density rho, cylinder of charge density rho plus sphere of charge density that charge density will be equal to minus 3 rho by 2. In this case, the important thing is how we are going to get this 3 rho by 2. So like I said, we are removing a sphere of charge density rho. So let me draw approximately. Suppose this is a cylinder, and from this cylinder we removed a sphere. The cylinder was having a charge density of plus rho, so this cavity is obviously going to have a charge density of minus rho, and we are filling this cavity with another material whose charge density is minus rho by 2. So therefore the total charge density that will be associated with this cavity will be equal to minus rho and minus of minus rho by 2, or we can write it like this: minus rho plus minus rho by 2, and this gives us minus 3 rho by 2, which we have used here. So this is the basic premise, this is the basic, you can say, concept behind the solving this particular question. Now let's come back to our cylinder first part. So first we are going to solve this particular first part, that is our for infinite, our charge cylinder, and you can say electric field of an infinite charge cylinder. Field of a infinite charged cylinder, and that is our standard formula. We already know that for a infinite charge cylinder, let us suppose its electric field is given as E cylinder, and that will be equal to the charge density divided by 2 epsilon naught, and the I forgot to write one thing: field of a infinite charge cylinder one second. What field inside? I won't write the field inside the infinite charge cylinder, and this will be equal to our R perpendicular, and we know that this R perpendicular will be equal to our xi plus yj. Therefore we can write that electric field because of the cylinder will be equal to rho 2 epsilon naught xi plus yj. So this is the electric field, and that is our standard formula. So let me draw the basic figure according to the question. So we are given that this is our suppose z axis, and this is our x axis. So we are given that our cylinder is, let us suppose, of this much width, and inside this we are going to carve out a sphere whose radius is given as a. So this radius is our a 0, 0, and so we can just carve out this sphere, and please remember this sphere is inside the cylinder. So we are having the sphere of radius a. And so we considered a point on a cylinder, and let us suppose it is at a distance r. Therefore we can say that its electric field, because the cylinder at this point P will be equal to our rho 2 epsilon naught and xi plus yj. Now for the same point we are going to find out what will be the electric field due to the uniform charged sphere. So now we are going to find out the field of a uniform charged sphere, and let us suppose this field is given as E sphere. Then this E sphere will be equal to charge density, let us suppose that is rho prime 3 epsilon naught, and we have this as our r prime, and here this rho prime is the sphere charge density. Rho prime is our sphere charge density, and this our r prime, this is a position measured from the center of the sphere. Position measured from the center of the sphere. Center of the sphere. And in this particular case question, we are given that our center is at x is equal to a. Okay, that is given in the question. And like we said, our rho prime will be equal to minus 3 rho by 2. So we can substitute it. We know that our rho prime is equal to our minus 3 rho by 2, and we are given that the center of the sphere is at x is equal to a. We are given that center of sphere is at x is equal to a. Therefore we can write that our r prime will be equal to x minus a I unit vector plus y, and then we have our z unit vector, and we can simply substitute back into this sphere formula. So we get our E sphere will be equal to, this comes as our minus 3 rho by 2 and multiply by, and we get this as our, 1 second, yeah, 1 by 3 epsilon naught, and we have this as r unit vector, prime vector. So 3 and 3 are going to cancel out. This comes minus rho upon 2 epsilon naught, and this is our r prime vector. Now obviously we are going to use the superposition and we are going to add the fields. So you can say that total electric field will be equal to electric field because of our cylinder plus electric field because of the sphere, and we simply substitute them. We get this as our rho upon 2 epsilon naught xi plus yj minus rho upon 2 epsilon naught, and we have this as x minus a I unit vector plus y j unit vector, and we have z k unit vector. And from here we can easily see that our x and y terms are going to cancel out, because this will be coming as our x times rho 2 epsilon naught, and this will be coming as minus x 2 epsilon naught. Similarly for the y term also. Therefore we get that our E total will be equal to rho upon 2 epsilon naught, and we left with our A of I minus Z k unit vector. And so we were supposed to find in the xy plane. So obviously xy plane we can just extract the component from here. So you can say for xy plane we are going to get that our electric field in xy will be equal to our rho a 2 epsilon, and we have our I unit vector. So this question was little bit, you can say, unusual one, because usually we deal in such type of question, we remove something, create a cavity, and we do not add anything to it. But in this particular case we added a material whose charge density was equal to minus rho by 2. Therefore the total charge density of this cavity will be equal to the addition of the both. This is the only major difference. Rest solution is quite simple. Always remember, whenever we are adding removing, because it is removed from the cylinder, and cylinder was having plus rho as its charge density. So the cavity, we know that we are going to consider it as a negative of that charge density, and we added a material of minus rho upon 2. Therefore the net charge density of the cavity which is filled by the material will be equal to now minus 3 rho by 2. The rest of the solution is same. That's not going to change. Next question. Okay. In this case, it is asked that in a figure a sphere with radius r is centered at the origin. Infinite cylinder with the radius capital R has its axis along z axis, and an infinite slab with a thickness 2r lies between the plane z is equal to minus r and z is equal to r. The uniform volume charge density, volume density of these objects are rho 1, rho 2 and rho 3 respectively. The objects are superimposed on the top of each other, the densities add where the objects overlap. How should the three densities be related that the electric field is zero everywhere throughout the volume of the sphere? Okay, so basic figure is given to us, and we have cylinder, then we are having sphere, and then we have a slab. Okay, so we have to find out, and remember, nothing is being removed, everything is superposed. It means there is only addition, addition, and addition. There is no subtraction part in this. Okay, so this is like laying one above the other. Okay, first we have cylinder, then on that cylinder we placed a sphere, and then on that we placed a slab, and we are going to find out that electric field should be zero in the sphere. Okay, so it means a sphere is consisting of all the three parts. Sphere is consisting of the cylinder, portion of the cylinder, sphere is consisting itself, and a sphere is consisting a part of the slab. So we are going to find out the condition when the electric field inside the sphere is zero. Okay, so that's the basic question. Okay. So in this case, we are almost given everything, and diagram is pretty simple. It's not much of complication here. So we are going to consider that it is given that there is z-axis. Let us suppose this is our z-axis, and this is our x-axis. We do not need x-axis, but still we assume it in order to find out the center. So we are going to consider the center of the sphere as the origin, and upper end is our, this slab is our plus r, lower end is our minus r. And we have to remember that nothing is being removed, so all the objects overlap with each other. So this is because in the question it is mentioned that objects are superposed. Okay, so they are overlapping with each other. So this is the important point here. Okay, you can see objects overlap. So if the objects are overlapping, so densities are going to add. Densities are going to add. And in this particular case, we have to find out with respect to the sphere. So for sphere, everything is overlapping. Okay. So this is sphere. It consists of part of the cylinder. It is also consisting of part of our slab. So therefore, we can say that we are interested in the sphere, and this sphere is consisting of part of a cylinder. It is also consisting itself, that is a sphere, and it is also consisting a part of a slab. So, and the densities are given rho 1, rho 2, rho 3, and we have to find out the condition such that this sphere is having a net electric field which is equal to 0. So it means their entire summation should be such that the electric field is equal to 0. We are going to find out the relationship between rho 1, rho 2 and rho 3, which gives us that electric field should be equal to 0. So this is the basic question. And so let us start with our uniform charge sphere. Okay, one by one we are going to take all the three objects independently, and then we are going to use superposition. So we are going to start with our electric field inside a uniformly charged sphere. So we are going to take field inside a uniformly charged sphere, and for that we are going to consider a Gaussian surface. We already know the formula, but let us make a little bit of understanding of that also. So we are going to consider a Gaussian surface whose radius is our small r and which is less than our capital R. Okay, because we are dealing with inside. So it means if this is our sphere, the center of the sphere, and r is our radius of that, so we are going to consider a Gaussian surface which is very close to the outer surface, little bit inside, and its radius is given as small r. Therefore we can write that the charge enclosed by the Gaussian surface let us call this as Q enclosed, that will be equal to our density is given as rho1 and multiplied by the volume, that is about 4 pi r cube. And from Gauss law, we can write that our electric field and our area will be equal to our charged enclosed divided by epsilon naught. So therefore we get that our electric field will be equal to, this will be our 1 upon 4 pi r square 1 upon epsilon naught rho 1 4 by 3 pi r cube, and we can cancel this 4 pi square goes by cube. Therefore we get that electric field will be equal to, it is rho 1, so we get this as rho 1 multiplied by r divided by 3 epsilon naught. We can write it in the vector form also, because that is very much required. Then we can easily find out when it will be equal to 0. So you can say in vector form, we can write this our electric field of the sphere, magnitude we already know is our rho 1 upon 3 epsilon naught, and our all the x coordinate, y coordinate, and x, y, and k, z coordinate. So this is the vector form of our sphere. Now we come to our uniformly charged infinite sphere. In this case also we are going to write that our field inside the uniformly charged infinite cylinder. And we are going to consider a Gaussian surface whose radius is small s. So we can just draw. So this is suppose our original cylinder, infinite. This is the axis of the cylinder, and we consider a Gaussian surface which is inside and very close. So this is the Gaussian surface, and our cylinder is having a radius of capital R, and we consider a Gaussian surface whose radius is small s. And it is along our z-axis. Therefore we can say that cylindrical Gaussian surface of radius s Gaussian surface of radius s, and this s will be our less than capital R, okay, because it is inside. And we can also write that this s will be equal to our x square plus y square, and that will be also our less than r. Now we can easily find out the charge enclosed by this Gaussian surface. We can say our enclosed charge, that is our Q enclosed, will be equal to density is given as charge density is our ρ2, and this comes as pi s square, and let us suppose length is our capital L. Now we can use our Gaussian law. So we have our Gaussian law, which gives us electric field, and this is our 2 pi SL will be equal to our charge enclosed by the epsilon naught. Charge enclosed is our ρ2 pi s square L, and this comes as our epsilon naught. And here this pi s square and L cancel out. Therefore, we get that electric field will be equal to our ρ2 multiplied by s and divided by 2 epsilon naught. And similarly, and we know that its direction will be radially outward in the xy plane. That will be radially outward in xy plane. That will be the direction. And in vector form, we can write this as our magnitude is our ρ2 as 2 epsilon naught, and this is only in xy plane, so this comes as x and our y unit vector. Now we come to our third part, that is our slab. So this is our field inside a uniformly charged infinite slab. Field inside the uniformly charged infinite slab. And we know that the slab occupies is between minus r and plus r. That is given to us. So this is our z-axis, and our slab is this one. So it is between plus r and minus r. You can see that our slab is between minus and plus r. So we are going to consider a Gaussian pillbox of area A, and that is going to extend from minus z to plus z. And we have to remember that the Gaussian we are going to consider a little bit inside. We are going to consider a Gaussian pillbox of area A. Okay. And this is our plus z, and this is our minus z. You can say Gaussian pillbox of area A extending from minus z to plus z with our z is less than r. Therefore, we can write the enclosed charge that is our Q enclosed will be equal to our density is given as ρ3 multiplied by this will be 2z times A. Now we can easily find out the flux, and flux will be for the field to be pointing along z unit vector. So we know that our field points along our z axis. Therefore, we can write our flux will be equal to our z times area and z times area, okay, because there are two surfaces, and that will be equal to twice Ez times A. Now we can easily use our Gauss law. We have our Gauss law, and this gives us our 2 Ez times A will be equal to the charge enclosed rho 3. This is 2Z A upon epsilon naught, and our 2 A cancels out. Therefore, we get that our electric field is equal to, we have this as our rho 3 times Z, and this is epsilon naught. And vector form, okay, it is not a big issue because it is only in Z direction. So we get a vector form of this will be equal to our rho 3 Z 2 epsilon naught, and we are having this as Z unit vector. So we got the electric field of all the three surfaces, okay, and we are interested in finding out what will be the net electric, what will be the condition such that the net electric field inside the sphere is equal to 0. So now we are going to find out the superposition of all the fields. We are going to algebraic add all the fields inside the sphere, because sphere is common to all the surfaces. Sphere is common to the slab, and sphere is also common part of our cylinder. Therefore, we can say that superposition of all fields, and from here you can say inside the sphere, let us call that field as E. So this field will be equal to field because of the sphere itself plus field because of our cylinder plus field because of our this slab, and we substitute all the values. So we get this our electric field is equal to 0 2 epsilon naught, and we are having this our x, y, z plus rho 2 upon 2 epsilon naught, and we are having our x and y, and finally we are having our z. Z means slab, rho 3 and 2 epsilon naught, and this is our z and z unit vector. Now we can just combine them with specular components. Okay. We are going to combine x and y because it is the same plane, and z we are going to keep as independent. So let us group the components. And for that we are going to use first our xy, and that gives us 1 upon epsilon naught. This is 1 upon 3 plus rho 2 upon 2, and this gives us x and y, and then we are left with our z. So we get this as 1 upon epsilon naught rho 1 upon 3 plus rho 3 upon 2, and this is our z. Now the question, it is asked that we want that electric field should be equal to 0. So we are going to impose that our electric field should be equal to 0. And we have three coordinates x, y and z, and all the three coordinates are independent of each other. So each coefficient individually must be equal to 0. So we want that our electric field should be equal to 0. So therefore we are going to use our xy is equal to 0. So we are going to get this as our rho 1 upon 3 plus rho 2 upon 2 is equal to 0. From here we get our rho 2 is equal to minus 2 by 3 times rho 1. And then we are going to impose same condition in our z is equal to 0, and we are going to get this as a rho 1 upon 3 plus rho 3 upon 2 is equal to 0, which gives us that our rho 3 is equal to minus 2 by 3 times rho 1. Okay. So it means the electric field should be 0 everywhere inside the sphere. Okay, that was our condition. This E means electric field inside the sphere should be equal to 0. And by this electric field we mean that the total electric field, and that total electric field will be the effect of the electric field because of the sphere, electric field because of the cylinder, as well as electric field because of the slab. So this will be our total electric field, that is a superposition of all the individual electric fields. And from here we get the condition is our rho 2 is equal to rho 3 is equal to minus 2 by 3 times rho 1. So this is the relationship between their respective charge densities, so that we get the electric field inside the sphere as 0. Next question. It's almost same, okay, but the question is framed directly, okay, but it can be asked in an indirect way also. Here the question is framed, and it states that consider one second, there is a mistake. Okay, consider a uniform ball of charge q, should be there, located entirely inside a larger sphere of radius r. Let the ball's radius be b. Let its center be located at a radius a in a larger sphere. Its volume charge density is such that its total charge is q. Assume that the ball is superposed on the top of the sphere so that all of the sphere's charge is still present. Can the force on the ball be obtained by treating it like a point charge and considering only the charge in the larger sphere that is inside the radius a? Indirectly it is asking how the force equation can be framed, and it is directly mentioned that the force will be same as the force because of the point charge. Here directly the hint type is given in the question, but it means that we have to find out what will be the force on the ball. That's the basic question. And second B part, would the force change if we instead remove the charge in the larger sphere where the ball is? So part B is simply removing the part of a sphere. And so in this question we are given lots of things, so let us figure it out. So we are given a larger sphere, and larger sphere, its radius is given to us, radius is of r, and its volume charge density is of rho. Then we are having a small ball, and this small ball we are having you can say a radius b, And in this case, we have to remember that the small ball center is located at a distance a from the center of a larger sphere. We can say radius b, and center is located at a distance a from the center of larger sphere. From the center of large sphere, and we are given that the total charge, radius is b, and we are given the total charge q is there. And in this case, it is not mentioned in the question, but we are indirectly given that the sphere is the ball is entirely inside the sphere, so we are going to use that the a plus b is our less than r. Okay. So it means ball is entirely inside the sphere. So we can just draw the figure approximately. So we are having a sphere, and let us suppose these are the, so this is our center of the sphere. It doesn't look like. And this is suppose center, and we are given that the ball is at a distance a from the center of the sphere. Suppose this is point A, so this distance is given to us over A, and here we can just draw a ball of radius b, and this is a ball of radius b, and we are given a sphere of radius r. So this is the basic question. And in the part A, it is mentioned that the ball is superposed on the top of the sphere in the part A. So we are given that our part A, ball is superposed on the top of the sphere. So it means the ball is added on the top of the sphere, and which we can also say that the original sphere charge still present everywhere. So these are the two things from here. So we can say from here that ball is added on the top of the sphere, top of the sphere, and we can also say that sphere's original charge is present. Okay, it goes nowhere. And so let us find out for part A. We are going to first of all find out what will be the electric field because of the uniformly charged sphere of radius small r, because of using the same by Gauss law. Okay, we can just directly write the formula for that. We can say that inside a uniformly charged sphere, And please remember that the charged sphere is having a radius of capital R. The radius is given as capital R, and its density, charge density, is given as rho. So we are going to find out inside, and for inside we are going to take a Gaussian surface of radius small r, which is less than capital R. Therefore we can write that electric field, because of the sphere at a distance r, will be equal to rho upon 3 epsilon naught, and this is r unit vector. Like I said, this is for r is less than capital R. And because of this electric field, we are going to find out what will be the force that will be on the ball, because of this electric field, because it is, the ball is put on the top of the sphere. So from here we can say that force on the ball, force on the ball, and force on the ball with charge density let us call this a rho ball, because it is rho ball, and total charge Q, total charge Q, and its center is given at A, centered at A, centered at A. Therefore we can write that our force will be equal to the integral of our charge density of the ball and the electric field because of the sphere, and d of r. Okay, that's our standard, you can say, formula how to find out the force. Okay, we are going to consider a small portion which is having a force of dF, and then we can extend to the total force, okay, which we already know how to do it. So this comes as rho upon 3 epsilon naught, because E sphere we already found out, and this is our charge density of the ball, and this is our, one second, yeah, r dr. Now we are given that we have a uniformly charged ball whose center is at A. Okay, that is given to us. So we are having a uniformly charged ball, and which is centered at A. Therefore we can calculate its integral part. So we can see integral of our density of our ball, and this is our r dr will be equal to charge multiplied by the radius, that is our r, in this case is our A unit vector. Therefore we can write that our force will be equal to rho upon 3 epsilon naught charge and our A unit vector. Okay. And this is nothing but the force of a point charge Q at R is equal to A. This is nothing but our force this is a force, a point charge Q at distance r is equal to a would fill inside a uniformly charged sphere. Inside a uniformly charged sphere, and which is only dependent upon the, you can say, the charge inside of the radius a, because this q is given as a charge of the sphere, not the charge of the ball. So it means we can treat the ball as a point charge at the center. That was the part A. And part B, now it states that instead of ball there is a cavity. So in part B we are going to solve for the same force, but here we are given that our ball in a cavity. So what is going to change? And so it basically means that previously there was a sphere and there was a ball. Now that was part A. Now in this case we are having a sphere, and in this sphere we created a cavity, and in this cavity we have placed a ball. Okay, that's the major difference between the two. So this is part B. So in first part there was our sphere and we are placing the ball directly on the sphere, but in part B we have sphere, we created a cavity, and then we placed the ball. So we are going to say how the difference is going to, whether the difference between the force is there or not. So let us say that we are having a full sphere and whose charge density is over rho, and then we are having a cavity, and that cavity we know is going to have a charge density of minus rho, and in that cavity we are going to place a ball. Place the ball in the cavity. And place the ball in the cavity, and the ball charge is having q of charge, that is our q. Okay, so this is our basically 3 steps. Usually what we do, we solve only the first 2. That's a normal question. We took the sphere and we created a cavity. Okay, but in this case we are going to place a ball of charge q inside that cavity, and this is almost same as our first question. Okay, but here we are going to find out a field. In the first question we found out our this electric field. Here we are going to find out the force. So let us solve this. So we are going to start with our field of full sphere, okay, which we already know. So we can say electric field of full sphere, and electric field our full at a distance of our r will be equal to rho upon 3 epsilon naught, and we have this as r vector. Now we have our negative sphere of charge density. We have sphere of negative charge density. So we have a field of the negative sphere. Charge density is our minus of rho, okay, which is making a cavity. That makes the cavity. and therefore the electric field due to this, let us call this as a E minus, at the same distance our R will be equal to minus rho upon 3 epsilon naught, and this is our R minus A. Okay. That is inside the small sphere. And from here we can find out the actual field of a charged sphere with cavity. So now from here we can find out the actual field of the charged sphere with cavity. And we can write this as E cavity for a position vector R will be equal to the superposition of both, that is our full plus removed of the cavity. And we can substitute it. We get this as our rho upon 3 epsilon naught R unit vector minus rho upon 3 epsilon naught, and this comes as R minus A unit vector. Obviously, if we open the bracket, this R and R goes away, and this comes as rho upon 3 epsilon naught, and we have our A unit vector. Here we can clearly see that our electric field, because of the cavity, is independent of our R. It is only dependent upon the A. So we can say which is uniform inside the cavity. It's not dependent upon R. Now from here we can say that because the charge is our Q, if we can say the ball which is having a charge Q in the cavity sees a uniform field in a cavity, see a uniform field and that uniform field is our E cavity rho upon 3 epsilon naught and our A unit vector. And we can find out our force now, because the ball is having a charge of Q. Therefore we can say that our force will be equal to F Q times E cavity, and this comes as our rho upon 3 epsilon naught Q A unit vector, and this is same as our part A. Okay, so in this particular question, that's the third one, answer was inside the question itself. Okay, so we are supposed to find out what will be the value of the force, and it is mentioned that it will be like a point charge behavior. Okay, but basically the purpose of solving this question is how the superposition is going to work when we remove something and when we add something. Okay, so first question was about removing and from a sphere, then adding, but with a different charge density. Okay. In second question, we did superposition of three things. Okay. So we were having you can say cylinder, and then we were having a sphere, and then we were having the slab, and all were superposed. Superposed means everything was adding, nothing was removed for that. That was our part B. And in that case we are supposed to find out, because they were having different charge densities, we are supposed to find out what will be the charge density ratio. The electric field inside the sphere should be equal to 0. And in third part, we were having a sphere, and in the part third was having two parts. In part A, we were having a sphere, and that on that sphere we simply placed the ball, and that was part A. And part B, we were having a sphere, same sphere, but then we created a cavity, and inside the cavity we placed that ball. Okay, that was our part B, and we found out the value of the force in both the cases is equal to same, like a point charge behavior is there. Okay, so this was our superposition of our electric fields, how they are going to behave. So this completes all the three